Hi, in this video, we are going to start our new section, which is on coordinate geometry. So we'll look at some problems on all of the topics of coordinate geometry that you need to be aware of. So we'll start with straight lines and then we'll move on to circles, parabolas, hyperbolas, and ellipses. So let's begin with some problems on straight lines. We know basic theory for straight lines. The standard equation is ax plus by plus c equal to 0. This is a linear equation in x and y. This everyone should be familiar with. Also, we have things like distance formula in the coordinate plane, distance formula, which tells us the distance between 2 points in the xy plane, and section formula, which tells us how to find a point which divides a segment in a given ratio. These are all standard things that you are probably aware of. We also have formula for the area of a triangle. Area of a triangle, if the 3 points are xa, ya, xb, yb, and xc, yc. These are 3 points in the xy plane. The area of a triangle using these 3 points will be given by this determinant: 1 xa, ya, 1 xb, yb, 1 xc, yc. Now this determinant can have a positive or negative value, so we put an absolute value sign outside here, and that gives us the area of the triangle. And in case the 3 points are collinear, then the area of the triangle must be 0 for collinear points, because there is no triangle formed when the 3 points are collinear, right? There are other forms of the straight line equation. There is the form y is equal to mx plus c, which is the slope intercept form. There is also intercept form, which is like this. And there is the normal form, which is x cos alpha plus y sin alpha is equal to p. These are all things that you have probably read in your lower classes. So we'll not spend too much time discussing the theory. In case you want to look at it in more detail, you should follow S.L. Loney's coordinate geometry textbook. That is a very good book. It's a classic text, and all of the theory that we require is present in that book. So that is a recommendation from my side. Use that to learn more about coordinate geometry. In this video, however, we'll look at some nice problems and understand how to apply this knowledge, right? So we'll look at the first one now. Okay, so the first question is this: a lattice point in the xy plane is a point whose x and y coordinates are integers. We have to prove that three lattice points cannot constitute the area or cannot constitute the vertices of an equilateral triangle. So the question is, if you take three lattice points in the xy plane, you cannot make an equilateral triangle out of them, right? So we have to think of a way to prove this. So let's think of the area. Let's say the vertices of the equilateral triangle are given by these coordinates: xa, ya, xb, yb, and xc, yc. Let's say these are the three vertices. Obviously, xa, xb, ya, yb, xc, and yc all are integers, right? That is why these are lattice points. Lattice points are points where both the coordinates are integers. right? So in this case, let's calculate the area of this triangle. So area should be by the determinant. It should be this 1xa by a, 1xb by b, and 1xc by c. This determinant will be the area. Now think about it, since each of these numbers are integers, the value of the area will be a rational number. It will be an integer if the determinant is even, and it will be a rational number if the determinant comes out to be an odd number, right? It is guaranteed that the area of this triangle should be a rational number, right? Also, since we have been given that this triangle is an equilateral triangle, so since it is an equilateral triangle, the area can also be written as root 3 by 4 a square, where a is one side, right? Root 3 by 4 mod of, let's say, ab square, right? So what is ab square? It is root 3 by 4. ab square by distance formula should be xa minus xb whole square plus ya minus yb whole square. Now, this area, if this triangle was equilateral, you can see that this term is an integer, and when you multiply it by root 3 by 4, this area is coming out to be irrational. So now you can see that we have a simple contradiction. When you use the determinant method, the area should come out to be rational. And when you use the formula for area of an equilateral triangle, you are getting root 3 by 4 a square, which is irrational. So because of this contradiction, we know that there are no such triangles, no such equilateral triangles with three lattice points in the xy plane, right? So we have arrived at a contradiction, and we have shown that it cannot be an equilateral triangle. These three vertices could form a triangle, but it cannot be equilateral, right? So that is the simple proof for this first question. A nice idea, because you would not have thought of area otherwise, right? So we have gotten the area in two different ways, and we have established a contradiction, right? Let's look at the next one. Now, again, this question says, in a coordinate plane, a triangle with all three vertices as lattice points. Again, lattice point is vertices where x and y coordinates are both integers, is called an integral point triangle. Integral point triangle. Because all of its vertices are integral, therefore it's called an integral point triangle. Now the question is, find the number of integral point right angled triangles OAB which have in center I as 2015, 7 times 2015, O as the origin, and right angle, and O is the right angled vertex. So basically what we have to do here is find the number of right angled triangles OAB where the right angle is at O and the in center is at the known coordinate of 2015, 7 times 2015, right? So let's draw a rough figure. Let's say this is something like this. This is O, this is A, and this is B, and this is my line for the in center, and the in center is somewhere here, I, right? So I is supposed to be 2015 comma 7 times 2015. So I lies on the line y is equal to 7x. That is obvious from the coordinate, right? And we know that angle BOA is equal to 90 degree. We have to find the number of possible triangles which are lattice point or integral point triangles. So A and B have to be integers, right? Okay. So now we know that y is equal to 7x is the line for the in center. So let's assume that this angle is alpha. So we know tan alpha must be 7 because the slope of that line is 7, right? Y is equal to mx. So this angle is 7. So if tan alpha is 7, what is the angle that OA line makes? This line will make an angle of alpha minus pi by 4. Why alpha minus pi by 4? Because in center will lie on the angle bisector. OI is angle bisector of BOA. So therefore, we know that angle IOA is equal to pi by 4. So angle AO and x-axis. So angle AOX should be alpha minus pi by 4. So that is obvious. So we know the slope of OA now. Okay, because we know tan alpha is 7. So the slope of OA, MOA, would be tan of alpha minus pi by 4. And that comes out to be tan alpha minus 1 by 1 plus tan alpha, which is 7 minus 1, 6 by 1 plus 7, 8. So that is coming out to be 3 by 4. So the slope of OA line is coming out to be 3 by 4, and therefore the slope of OB line should be minus 4 by 3 because OB line is perpendicular to OA line, right? Okay, so both of these lines are passing through the origin. So we can say that this line equation should be y is equal to 3 by 4x, and this line equation should be y is equal to minus 4 by 3x, right? So we have gotten this information now of OA line and OB line. So parametric points on A or the coordinates for A and B we can write in terms of two unknowns. So let's do it on the next screen. We know OA line is y is equal to 4 by 3, not 4 by 3, y is equal to 3 by 4x. This is O, this is A, and B was like this, OB. So A point can be written as 4t1 comma 3t1, right? A point can be written as 4t1 comma 3t1 because it satisfies this line equation. And similarly, OB line was y is equal to minus 3 by 4x. So B point can be written as minus 3t2 comma 4t2, right? And O is the origin, right? So from this, what we get is we get the distances of OB and OA, right? OB is basically 5t2 and OA is 5t1, right? Now T1 and T2 can be integers. T1 and T2 are some integers. They don't necessarily have to be equal. And why are they integers? Because we know that B and A are integral points, right? Correct. And this was my OI situation. This is I, right? So since this is the in center, we can say that OI, and this is 45. So OI sine 45 is equal to in radius, right? This perpendicular is my small r, right? So we can say OI sine 45 is equal to the in radius small r. Therefore, OI by root 2 is equal to small r. And I point was given as 2015 comma 7 times 2015. So what is OI? OI is 2015 square plus 7 square into 2015 square root over that. So that is 2015 into 1 plus 49 is 50. So it is 5 root 2. This is my OI. And therefore we get the value of R. The value of R is coming out to be this divided by root 2. So 2015 into 5. This is known to us that the in radius is now coming. It is 2015 into 5. Also, in a right angle triangle, we can show that R will be equal to OA plus OB minus AB by 2. How do we get this result? R should be equal to this. So let's think about this. This is simple geometrical result. Let's take a right angle triangle. Let's say this is O, A, and B. And I want to draw an incenter. So let's make an I here somewhere. And I have a circle like this. This is my in circle. The figure is not accurate, but you get the idea. This distance is R, perpendicular, and this distance is R. So this much is R, and this much is also R. And therefore, this distance is OA minus R, and this distance is OB minus R. And because B and A are points from which external tangents are being drawn to a circle, this tangent length is equal to this length. So this length till here is, which is the point of tangency on the side AB. This length is OB minus R, and this length is OA minus R, right? And so therefore you can say that AB should be equal to OB minus R plus OA minus R. And from here we can get R is equal to OB plus OA minus AB by 2, right? Now this gives us a good equation. We can say AB was equal to OA plus OB minus 2R. So AB square should be equal to OA plus OB minus 2R whole square. And AB square, since this is a right angle triangle, AB square is what? By Pythagoras theorem, it is OA square plus OB square is equal to OA square plus OB square plus 4R square minus 4ROA minus 4ROB plus 2OAOB. So OA square and OB square get cancelled from both sides. And what we have is this result. 4R OA plus OB minus 2 OA OB is equal to 4R square, right? Correct. Now we know that OA was equal to 5T1 and OB was equal to 5T2. And we know that R value was 5 times 2015. If you recall from the previous screen, we had calculated all this. So let's put that now here. This is 4R. OA plus OB is 5 times T1 plus T2, right? And minus twice of OA into OB. That's twice of 5T1 into 5T2 is equal to 4 times R square, which is 5 square into 2015 square, right? And this was 4 into 5 square into 2015 T1 plus T2 minus 2 into 5 square into T1 T2 is equal to this, right? Correct. So actually I don't think I needed to expand this. This doesn't help us a lot. We can write it directly from here, I think. We have this relation, right? So I will just use that now. AB square is equal to OA plus OB minus 2R whole square. And I can say AB square was what? OA square plus OB square. OA square plus OB square is equal to OA plus OB minus 2r whole square. And OA square was 25 T1 square plus 25 T2 square is equal to 5 T1 plus 5 T2 minus 2 into R, which is 5 times 2015. So what we can do is take it, and this is whole square, so we can take 5 common from all the terms and we get 5 square T1 plus T2 minus 2 into 2015 whole square, and this is 25 T1 square plus T2 square. So we can cancel the 5 square and 25 and we are getting this equation. T1 plus T2 minus 2 times 2015 whole square is equal to T1 square plus T2 square. Right? Okay. So in order to figure out how many such triangles are possible, we need to find how many possible roots are there for this equation with T1 and T2 being integers, right? So in order to simplify this, we can say we can create new variables. Let's say x is T1 minus 2015. Let's say y is T2 minus 2015, right? So then this part becomes x plus y whole square is equal to T1 square plus T2 square. So that is T1 is x plus 2015 whole square plus y plus 2015 whole square, right? Now we simplify it. We will get 2xy here because x square plus y square will get cancelled. You will have 2xy is equal to 2 into 2015x plus 2 into 2015y plus 2 into 2015 square, right? This is the equation that we are getting. Now 2 can get cancelled from every term here and we end up with the equation xy is equal to 2015x plus 2015y plus 2015 square. And we have to find the number of possible solutions for this equation where x and y are also integers like t1 and t2, right? So this can be solved by factorizing the x and y terms. So I have brought everything here. I just need this is equal to, I need a plus 2015 square. So that will become root times 2015 square. What have I done? I have taken this term to the left hand side and I have added a 2015 square and made it 2 times 2015 square here. Why? Because this will help me factorize x common y minus 2015 and minus 2015 common y minus 2015. So we are getting x minus 2015 multiplied by y minus 2015 is equal to 2 times 2015 square, right? Okay. Now from here, what we can see is 2 times 2015 square has factors of 2 into 5 square into 13 square into 31 square, right? We want to write this number as a product of two different factors, right? Product of two different factors. So how do we count the number of possible divisors or number of possible divisors of 2 into 2015 square? That is a standard combinatorics problem. We can say the prime factors are 2, 5, 13 and 31. The number of possible pairs that satisfy would be 1 plus 1 into 2 plus 1 into 2 plus 1 into 2 plus 1. Why? Because the power of 2 here can be 0 or 1. The power of 5 could be 0, 1, 2, 3, 0, 1 and 2. And similarly for 13 and 31 also. So there are three options for powers of 5 and 13 and 31. And two options for powers of 2. So there are 54 possible pairs. How do we get pairs here? Because when we make a divisor, we will say let's say power of 2 in the divisor was 0 and power of 5 was 1 and power of 13 was 2 and power of 31 was 1. Then as soon as we have made this divisor, the rest of the prime factors go in the other divisor. So every time we choose one of them, we are getting the other one as well. So 54 possible pairs are there. Once you have these 54 pairs, there will be 54 possible values of x and y. And as soon as you get x and y, we can write the values of T1 and T2. And as soon as you get T1 and T2, you are getting different triangles OAB. So ultimately, you are getting 54 different triangles OAB that satisfy this condition. So that is an interesting question when we were given the in-center location of a right angle triangle OAB, and it was given that the coordinates of A and B were integral points, and then we are counting the number of possible triangles. Eventually, the question boiled down to solving an equation and finding how many integer solutions are there, right? How are we getting that? We are getting product of two factors is equal to some number. So we are saying how many possible ways we can do that. So that is the number of divisors of this, right? So 54 possible pairs of triangles we are getting. So that was question number 2. Let's look at the next one. Question 3. So here we have, suppose the equation of a straight line, M is y is equal to kx plus 1. Let A and B be 2 points on line M whose horizontal coordinates, whose x coordinates are the two distinct negative real roots of the equation 1 minus k squared x squared minus 2kx minus 2 equal to 0. Now let a straight line L pass through minus 2 comma 0 and the midpoint of segment AB, and let CD be a line segment on the y-axis. Line segment on the y-axis. Consider all possible straight lines L that have no common point, with CD. Find the maximum possible length of CD. That is the question. Think about it. What is the question saying? We have a situation like this. Y is equal to kx plus 1 is a line. A and B are 2 points on the line M whose x coordinates are the negative real roots of this equation. Okay. So line M, let's say line M is like this. This is M. A and B are 2 points on line M whose x coordinates are the negative real roots of this equation. Let's say this is A and this is B. Right? A straight line is drawn through minus 2 comma 0. Let's say this is minus 2 comma 0. And the midpoint of segment AB. Midpoint of segment AB is here. Let's say. And this is my line, straight line L. Right? This is my straight line L. And let CD be a possible segment on the y-axis. CD is a possible segment on the y-axis. Let's say this is the segment on y-axis, CD, right? Consider all possible straight lines L that have no common point with CD, right? So right now if you can see the straight line L has no common point with CD, but if my line M was different, if my line M was different and the midpoint was here for line M, then it would have had a common point, right? So line M can change because A and B depend on the roots of this equation, right? So the line M and its orientation can change based on that. The straight line L always passes through one fixed point and the midpoint of AB. So straight line L depends on AB location, and therefore it will not cut CD. CD is a line segment on the y-axis. It will not cut CD only if A and B are such that it is above or below CD, right? So let's think about how we go about solving it. We have to find the maximum possible length of CD, right? Okay. So I'll do it on the next screen. We will say let A and B be x1, y1 and x2, y2. These are the 2 points A and B on the line M. So we know that x1 plus x2, sum of the roots from the equation was 1 minus k square x square minus 2kx minus 2kx minus 2 equal to 0. Right? So x1 plus x2 is coming out to be 2k by 1 minus k square, the sum of the roots. And midpoint of AB, let's call that M. And the x coordinates of midpoint M would be x1 plus x2 by 2. So that is k by 1 minus k square, right? And obviously M lies on line AB. M lies on AB line. And the equation of AB line is y is equal to kx plus 1. So y coordinate of M would be k times xm plus 1. And that can be calculated as k times k by 1 minus k square plus 1. So this becomes 1 by 1 minus k square. This is y of n, right? Okay, so we know the point M now. The point M, which is the midpoint of this, is given by k by 1 minus k square, comma 1 by 1 minus k square. Right. And we have a straight line L that passes through minus 2 comma 0 p. It passes through M, k by 1 minus k square and 1 by 1 minus k square, right? And we also have to ensure, we know that the straight line L will intersects y-axis, let's say at Q. So let's say Q coordinates are 0 comma b, right? So the straight line L will have some point of intersection with the y-axis, and that will be my Q point. So we know that P, M and Q are on line L, so they are collinear, right? P and Q are collinear points, and because they are collinear points, we can equate the slopes, right? We can say the slope of PQ should be equal to slope of QM, should be equal to slope of MP, right? Because P and Q lie on line L, right? Correct. So since P was minus 2 comma 0, Q was 0 comma B, and M was k by 1 minus k square comma 1 by 1 minus k square. Let's do the collinearity condition. So slope of PQ will be B minus 0 by 0 minus 2. So plus 2 is equal to slope of MQ would be 1 by 1 minus K square minus B by K by 1 minus K square minus 0. Right? So this becomes, if you multiply by 1 minus K square up and down, this is 1 by minus B 1 minus K square by K. Right? We are getting the relation B by 2 is equal to 1 minus B plus bk square by k, right? Okay, so if we simplify this a little bit, we will get bk by 2 is equal to 1 minus b plus bk square, and we can basically solve for b from here. So we'll get bk by 2 minus bk square plus b is equal to 1, which implies b is equal to 1 by minus k square plus k by 2 plus 1, right? What this tells us is the value of B. Now this tells us where the line L cuts the y-axis. Line L was the line like this. It cuts the y-axis at this point Q. So if we know the values of B possible, then we can see that where all the line L will pass through the y-axis, right? So wherever it doesn't pass through the y-axis, that is the possible region where we should make our segment CD, right? Because remember in the question, we wanted line L to not cut through CD. Right? So the possible length of CD will be wherever line L cannot cut the y-axis, right? So I will find the range of B. Range of B tells us what are the possible y-intercepts of line L, right? So that is pretty easy. But first we have to think about in order to find range of B, we need to figure out range of K, right? So we'll do it on the next screen now. We have B is equal to 1 by 1 plus K by 2 minus K square. And we also know that x1 and x2 are two distinct negative real roots of the quadratic equation 1 minus K square x square minus 2kx minus 2 equal to 0. So first thing is, since both the roots are negative, we have x1 plus x2 should be less than 0. So that should be 2k by 1 minus k square should be less than 0. That is the first condition. And we have x1, x2 should be greater than 0. So that means minus 2 by 1 minus k square should be greater than 0. And that implies that this denominator is negative. That means k square should be less than 1. This condition gives us k square is less than 1. Now, since it has two distinct real roots, the discriminant should be positive. And discriminant for the quadratic is 4k square plus 8 times 1 minus k square should be greater than 0. That becomes minus 4k square plus 8 is greater than 0. Or 8 is greater than 4k square. Or we get k square is less than 2. So we are getting these two conditions. Basically, this implies that 1 is less than k is less than root 2. This is the condition that we are getting on K. And now we need to figure out the range of B. So this is a simple quadratic. So we know the minimum value of this quadratic, right? You can do this calculation yourself. This is minus of K square minus K by 2 plus 1 B. And or you can just find maximum minimum of B with respect to K by doing calculus. You will realize that if K lies between 1 to root 2, then B has a range of minus infinity to minus of 2 plus root 2 union 2 to infinity. I will leave this part to you. This is a simple enough calculation. The parabola is a downward facing parabola, and you can find the value of the parabola, the maximum or minimum of the denominator, and similarly you can find the range of B. So you will realize that the range of B is this. And if this is the range, that means the straight line L can cut above 2 to infinity. The B point can be anywhere here above 2, or it can be below minus 2 plus root 2. Okay? This is 0 comma 2, this is 0 comma minus 2 plus root 2, and it can be below this. So all of these points, the line L can take values like this. Line L can look like this. So that means the CD segment must be between these 2 points, right? CD segment must be between these 2 points on the y-axis, because there cannot be any point of intersection of L and CD. So therefore the maximum length of CD maximum length should be 2 plus 2 plus root 2, which is 4 plus root 2. How are we getting that? The positive y-intercept starts from 2 and the negative y-intercept starts from minus 2 minus root 2. So the length of the possible segment CD is the segment between these 2 points, right? CD maximum value is 4 plus root 2. Okay. Now, in the next question, we are going to look at a tricky problem. I mean, it is pretty simple, but a nice idea. We have this question. Consider the set of all integral points on the xy plane and the set of all straight lines with rational slopes. We have to show that such straight lines will pass through infinitely many integral points. So we have a set of all the integral points on the xy plane and the set of all straight lines with rational slopes, right? We have to show that if any straight line passes through an integral point, it will pass through infinitely many integral points, right? So let's see, if L is a straight line with a rational slope, then its equation can be written as ax plus by plus c equal to 0. The slope here is minus a by b. We know that a and b are integers such that b is not equal to 0, because then the slope will be undefined. Slope has to be rational, right? Now we say let x1, y1 be an integral point on line L. That means x1, y1 are integers and ax1 plus by1 plus c equal to 0, right? What we have to show is that the line L will pass through infinitely many integral points, right? So how will we get infinitely many integral points? If we have one integral point of the line L, we have to get more. We have to get infinitely more, right? So I'll do it on the next screen. So think about it. We already know ax1 plus by1 plus c is equal to 0. And x1, y1 lies on L. Let's think of a new point. The point is a x1 plus k times b plus by1 minus k times a plus c. Let's calculate this value. This will come out to be ax1 plus by1 plus c plus akb minus akb, right? So this is going to be ax1 plus by1 plus c, and that is 0, right? So this implies that x1 plus kb comma y1 minus ka lies on line L. Now we know already that a and b belongs to integers. So if k belongs to integers, then this is an integral point. And now you can take so many values of k. You can start with 0 and you can do plus minus 1, plus minus 2, and so on. And always, as long as one integral point lies on the line L, we will have a next point that also lies on the line L, and that is also integral. So this construction basically tells us that if we have a straight line with rational slope and it contains an integral point, then we can always find infinitely many integral points which will lie on that straight line, right? So that concludes the proof. And that's all for now. We looked at a few questions and a few interesting questions with different ideas that you don't normally see in straight lines. We'll continue with more videos for the coordinate geometry part, the analytic geometry section of the syllabus, and we'll look at circles and other curves in the next few classes. So stay tuned for that, and I'll see you next time.